In this topic of study, we're going to focus on the structure of the Earth first. The Earth is made up of three main layers: the crust, the mantle, and the core. According to other resources, this can then be divided further into an inner and outer core and an upper and lower mantle. The crust is the outer layer where we have the mountains and oceans. So make sure you're aware that the oceans are on top of the crust. This is going to be over the thinner, more dense crust called oceanic crust. So we do have continental crust where we have the mountains above the ocean, and then we have the oceanic crust. Crust is then further broken down into pieces called plates. Now, more specifically, we're going to say it's the crust and upper mantle, which is the lithosphere, which is broken into those plates. The mantle. The mantle is a layer of the Earth between the crust and the core. The mantle is filled with magma, which is molten liquid rock, and this is the largest layer of the Earth. In this picture, you can see that the crust and upper solid mantle makes up the lithosphere. Then below that, we have the asthenosphere, and then we have the mantle. The mantle is made up of the lithosphere is solid, while the asthenosphere is going to be weaker and more pliable and more like a honey, or the outer core scientists believe is liquid and made up of iron and is very dense, while the inner core is going to be more of a solid material. You can take a look at this review. What are the four layers? Okay, focusing on plate boundaries. The Earth is made up of plates, which are the broken pieces of the lithosphere, and we believe that these plates do move, and the movement ties in with tectonics. So the forces that cause movement is the word tectonics. So we combine those two words, plate tectonics. These broken pieces of the lithosphere are forced to move in certain directions. Now, the Earth's crust is divided into 12 major plates, which moves in different directions. Sometimes they are moving away from each other, sometimes they're moving towards each other to the side, or maybe a different part of the plate would be doing multiple movements. Now, what do scientists believe causes the plate tectonics? This would be convection currents. So the heating and then rising, and then the cooling and sinking of the magma. So when the magma heats, it rises. When it cools at the surface, it sinks. This up and down motion would then move the plates, creating a cycle of magma. A great example of this would be floor heating. If we heat the floor and then the air rises, or even a convection oven. Here's another picture in which it shows the convection currents moving in different directions, causing the plates to move. So we did communicate that the plates are going to move. The pieces of the lithosphere are going to be moving. We do see evidence of that. The plates kind of float on top of the mantle, just like ice cubes on a bowl of water. And then basically they kind of fit together. Basically, we can look at these plates as if they fit together, or they maybe perhaps in the past fit together like jigsaw puzzles. Was there a Pangea, one world continent? Here you can see all the different plates, and you can see the continents above the plates or on top of the plates. So a lot of the plates are underwater, such as the Pacific plate, the Nazca plate. A lot of it is underwater. Okay, as I just said on the previous slide, what is Pangea? Pangea was believed to be that supercontinent. Okay, so is this an evolutionary theory, or could it be a biblical pre-Noah's flood landmass? It very possibly could be that this could have been what God created, and then after the flood, or during the flood, that they ripped apart very violently and were pulled away from each other. Not only when the flood happened, did water come from the sky, but it said that the floodgates from below came up. Could magma and other things just drastically happen very quickly? Yes, I mean, it's possible. There's no way for us to necessarily scientifically prove this. Okay, the Ring of Fire. The Ring of Fire is the area along the Pacific Plate where you have a lot of magma coming up because the plate boundaries. You have a lot of earthquakes in this Ring of Fire. In this picture, you can identify where the plate boundaries are. And this is going to lead into another picture that's going to go in a little more detail about the movements of the plates. But before we look at that, let's look at the types of plate boundaries. Here we have, if two plates are moving away from each other, think of diverge, moving away. Divergent plate boundaries move away. They divide, they separate. A convergent, to converge, to come together. Okay, that C word, come together, converge. They hit each other, they're coming together. And then transform means sliding past each other, they're rubbing past each other. A great example of this would be the San Andreas Fault in California. And we'll look at that later. Here's that other picture that I was talking about. As you can see, the plates are moving in different directions. You can see that by the arrows. If you look at the Pacific Plate, is moving more to the northwest, while the Nazca Plate, which is to the right of the Pacific Plate, is moving east into the South American Plate. The South American Plate is moving west. So the Nazca Plate and the South American Plate are hitting each other. And what's that going to create? Mountains. Okay, so that's going to be mountains. And you can actually see by the key at the bottom right that a divergent boundary has a certain pattern, which looks like a little space, a little white rectangle, while the convergent boundary has these little mountains, and a transform is just a line. So wherever you see those little mountains, that would be where they're hitting a convergent boundary, which is quite interesting that Japan is near a convergent boundary. Could Japan have been made by a convergent boundary? Maybe it was just pushed up. So let's focus a little more on divergent boundaries. You can see the plate is moving away. As the plate is moving away, magma rises, and then you'll have some volcanoes between those two divergent plates. Now, if you follow them along, we're going to eventually see that there's going to be convergence happening on either side. So there is a give and take here. Because of the spreading away, it will eventually hit perhaps another plate. Now, a great example of a divergent boundary would be Iceland. So you do need to know this real-life example. Iceland, if you look at the picture at the bottom, is slowly getting larger. There's lots of volcanoes, lots of earthquakes running through Iceland. Now, in the next unit, we're going to talk about a normal fault. We're not going to get into major detail about the movement of a normal fault, but you can actually see here that the large arrows at the top show that a normal fault is happening because of a divergent plate boundary. So basically, it's moving away from each other. So let's talk about what a fault is first. The fault is basically just the crack between the two land masses. Well, if you read what I wrote in the notes, it says a joint is the crack. Well, basically they're both the same thing. A joint and a fault are the crack, but a fault is when the land masses are then moving. So the joint is the crack, but when those land masses move along that crack or that break, then we call that a fault. So without it moving, the crack is the joint, but then when the land masses start moving, we call that a fault. Now let's talk about convergent boundaries. That's when they are converging, they're hitting each other. There are three types. There's continent-to-continent convergence or collision. There's continent-to-ocean crust collision. and there's ocean-to-ocean collision. With continent to continent, basically it's real easy, it's real basic. You just have one landmass hitting another one, and it's creating large mountains. An example of that would be the Himalayan mountains or the Alps. But continent to ocean crust collision, this is going to be where you have the oceanic crust hitting the continent. This is generally going to cause subduction when that oceanic crust gets pushed under the continental crust. You're going to have lots of mountains created on the continent side. A great example of that would be the Andes Mountains. And then the last one would be ocean to ocean collision, and you will have probably some mid-oceanic ridges, and it's going to be underwater. So let's take a look at some pictures of those three. Here's the continent to continent collision. You have the two land masses, the two continental crusts hitting each other, creating those mountains. And you can see the examples are the Alps and Himalayan mountains. Now, continent to oceanic crust collision, it's very clear that there's subduction happening. Basically, when the subducted oceanic plate goes under the water, goes under the continental crust, it starts to melt. That magma is less dense, then it rises and it pushes through into the mountains, and that actually creates volcanoes. So subduction means going under. A great example of this was South America. We said the Nazca plate going under the South American plate, and that's creating the Andes Mountains. And you can see that here. The Nazca plate gets pushed under, and you can see the Andes Mountains are all on that left side, that west side. There's no mountains on the right side because there's no plate boundary forcing those mountains to be created. Okay, then we have the ocean-to-ocean plate. A great example of this would be any mid-oceanic ridges or any trenches that are happening. Okay, the Mariana Trench would be a good example. Then we move into transform boundaries. This is when they're sliding past each other. They're not going away. They're not going towards. They're going different directions, but they're sliding past each other. A great example of this would be the San Andreas Fault. And if they're sliding past each other, there's a great probability that a piece of the rock may get snagged, causing stress and a buildup, then causing an earthquake. Okay, in a future chapter, we'll talk about earthquakes and volcanoes in more detail, but let's kind of tie in the connection. You specifically saw this with Iceland. As the plates are moving away, we have a lot of volcanic activity. You also saw this with subduction. So going back to the Ring of Fire, you can see all those red dots. That's where all those volcanoes are formed. Now, volcanoes are formed by three ways. We talked about subduction, when the oceanic plate goes under, and you can see that on the right and left side of this drawing. Okay, but then you also have rifting. Rifting would be in the middle. That's when it's opening, letting magma come up. And then the third way would be hot spots, and I'll talk about that in a second. So here's the subduction. Here's the rifting. So this is when the magma comes between your two divergent boundaries. And the last one would be the hot spot. So the hot spot stays still. This is not going to be at a plate boundary. This is actually going to be in the middle of a plate. A great example of this would be Hawaii. If I jump back to the previous pictures here, if you look at the Pacific plate, look at the very center of the plates. You have some volcanic activity. You have like one dot down here next to where it says Pacific plate, and then you have two dots higher up in the middle. That would be where you're having some volcanic islands. Those are where you're going to have hot spots. So that's where Hawaii will be, those upper ones. Okay, so you can see here's the hot spot forcing magma. The plate moves, making multiple islands. Now those other islands may get eroded and going underwater, but those islands are not going to be volcanically active.